In this online lecture, we're going to talk about the reactivity of coordination compounds. Specifically, we're going to talk about crystal field stabilization energy, reactivity, so the kinetics and thermodynamics of transition metal complexes, and the chelate effect. So last time we talked about crystal field theory, and we specifically talked about how we can use crystal field theory to predict the color and magnetism of coordination compounds. So in this lecture, we're going to start off by finishing our discussion of crystal field theory with crystal field stabilization energy. Next, we'll talk about the kinetics of coordination compound reactions, labile versus inert to substitution, and then the chelate effect and how it's entropically driven. And we'll talk about EDTA specifically and the applications of EDTA and other chelating agents. Crystal field stabilization energy is simply the stabilization once an ion is in a crystal field. So cobalt 3 plus has a D6 electron configuration, and we can imagine the isotropic case. So if there's no crystal field, this is our electron configuration. Once a crystal field is applied, so let's specifically say we have an octahedral field. And remember that this line is our barycenter, so the energy that we initially started out with. Our Eg orbitals are raised 3/5 delta octahedral, and our T2G orbitals have lowered -2/5 delta octahedral. So you could see if you multiplied 2 by 3 and 3 by 2 and summed all of the energies of all the orbitals together, they would equal 0, which is our barycenter. Okay, so crystal field stabilization energy is simply defined as the energy of the electron configuration in the ligand field minus the energy of the electron configuration in the isotropic field. So isotropic just means that it's spherically symmetric. So if we had spherically symmetric ligands, these would all be degenerate. But when they're specifically in the octahedral orientation, then we have our Eg orbitals higher and our T2G orbitals lower in energy. So let's assume that we're dealing with a high spin case. So if we calculated our crystal field stabilization energy, it would be the energy in the ligand field. So we're going to say that we have 4 electrons that have decreased by -2/5 delta octahedral and 2 electrons that have increased by 3/5 delta octahedral. And then we also have 1 pair of electrons. So we're going to add on a pairing energy. We're just going to call it Pe for pairing energy. Or you could even just call it P, just to represent that pair. And then if we subtract off, we would have minus P, again, just times 1 because we just have 1 pair. So if we sum that all together, we get an overall crystal field stabilization energy of -2/5 delta octahedral. So this means that because we're in this octahedral complex, this electron configuration is slightly more stable by -2/5 delta octahedral than this isotropic electron configuration. We could also imagine a low spin case. In the low spin case, remember delta octahedral is greater than your pairing energy, so all of your electrons are going to be in the T2G orbital. It's going to be most stable for the electrons to populate the T2G orbital and keep the Eg orbital empty. So in this case, crystal field stabilization energy, you take the energy of the ligand field, so that would be 6 electrons times -2/5 delta octahedral. We don't have any electrons in the Eg orbital, but we do have 3 pairs. So we need to add on those 3 pairing energies and then subtract off energy for the isotropic field where we have 1 pair. In the low spin case, we have a lot of stabilization from all 6 of these electrons going into this lower energy orbital, negative 12/5 delta octahedral. We do have some increased potential energy from the electron-electron repulsion in these d orbitals, in our T2g d orbitals. But we did already have 1 pair in the isotropic case, so we need to subtract that off. So this is the amount that's being stabilized, and this pairing energy is raising the energy a little bit for this complex. But overall, we know that delta octahedral is greater than our pairing energy. So overall, this is going to be a net stabilization. Okay, kinetics and thermodynamics of coordination compounds. So in order to talk about kinetics and thermodynamics, we need to review a few terms. So the first is delta H, or enthalpy. It's the heat transfer at a constant pressure. So we sometimes will use enthalpy and heat interchangeably because most chemical reactions that you will be doing are done under constant pressure. The next is delta S, or entropy. Sometimes we imprecisely call this the disorder, but a better definition is freedom of motion. So it's the disorder or freedom of motion change in a reaction, delta S. Delta G is Gibbs free energy. This is chemical potential energy, Gibbs free energy, but delta G change predicts spontaneity of a reaction. So if delta G is negative, it's spontaneous. If delta G is positive, it's non-spontaneous. We also talked about delta G naught. Again, we're talking about chemical potential energy, but when you're looking at Gibbs in the standard state, this predicts the favorability of the reaction. So favorability and spontaneity are very similar. The difference is delta G naught is related to your equilibrium constant. So as K is large or favors the products, then delta G will be negative. And delta G is equal to delta H minus temperature times your change in entropy. This came from the second law of thermodynamics, which we discussed last quarter. Okay, one thing that we need to remind ourselves is that spontaneity can be determined by delta G, but spontaneous reactions are not always fast. We talked about a lot of different examples last quarter. Rust, iron rusting, for example, is a spontaneous, slow reaction. So the speed of a reaction is not determined by delta G, but it's determined by the height of the transition state, which we call the activation energy, or delta G double dagger. So this difference in potential energy between our reactants and our products, this is delta G naught. So if this is negative, this is going to favor our products. And this difference in potential energy between our reactants and our transition state is what we call the activation energy, or delta G double dagger. Remember, as your activation energy increases, the speed of your reaction decreases. Just a quick survey of reaction types. This is just a small subset of different types of reactions for coordination compounds, but you'll be seeing some of these in the lab portion of the class. So the first is a substitution reaction. A substitution reaction, typically you do not have a change in oxidation state. It's just simply switching out the ligand. So we're going from tetra aqua copper 2, reacting it with 4 amine ligands to go to tetraamine. Next, we have dissociation reactions, and that just means that we have a decrease in the number of ligands. So we have, again, we don't have any change in oxidation state, but our coordination number is decreasing. So here, we're going from hexa aqua cobalt 2+, so this is octahedral. We're heating it up, and we're going to tetrachloro cobalt 2+. So this is now a tetrahedral or square planar complex. We can also have the opposite of a dissociation reaction, which is an addition reaction where your coordination number is increasing. So here we have tetrachlorotitanium 4 reacting with 2 chloride anions to form hexachlorotitanium 4+. So it's going from either square planar or tetrahedral to octahedral. Finally, we have oxidation reduction, or electron transfer. One of the complexes that we typically make in the lab is cobalt acac. Cobalt acac, this is cobalt 2+. We add hydrogen peroxide to oxidize it to cobalt 3. So here's just a little GIF of a substitution reaction from ChemWiki. And what I want you to notice here in this animation is that the first step of the reaction is the breaking of the metal ligand bond. Your activation energy is going to increase as the strength of your metal ligand bond increases. We introduced half-life last quarter, but in this context, we're specifically talking about the half-life of a substitution reaction. So it's the time it takes for the reactants to decrease in half of its initial concentration. We call transition metal complexes labile if their half-life is less than a minute, and inert if their half-life is greater than 1 minute. Something to point out is that labile and inert are kinetic terms. So they're specifically talking about the speed of the reaction, whereas stable and unstable are thermodynamic terms. We're talking about the chemical potential energy change of the products and the reactants. Again, this first transition state that we're seeing, this highest activation energy barrier, is this metal ligand bond breaking. So your activation energy is going to be greater for stronger metal ligand bonds. So the longer or weaker the metal ligand bond, the faster the reaction. Again, weaker metal ligand bond means smaller activation energy barrier and a faster reaction. To predict labile or inert, we need to look at the strength of that metal ligand bond. Okay, so notice this. Typically, first row of the transition metals will be labile to substitution. Major exceptions are chromium 3+ and cobalt 3+. We'll talk about that in just 1 second. Whereas second and third row transition metals are inert to substitution. So remember when we were talking about size of the metal last week? So what we talked about last week is if you have a large metal, your ligands can approach closer to the metal. This is going to be a shorter metal ligand bond. So your smaller metal is going to have some steric hindrance from the ligands. So smaller metals will form longer metal bonds, which will be weaker. Typically, first row transition metals are labile to substitution. Second and third row are inert to substitution. Major exceptions, chromium 3+ and cobalt 3+. So chromium 3+ has a D3 electron configuration. And what that means is that our crystal field stabilization energy is going to be pretty substantial. It's -6/5 delta octahedral. And so because of this increased crystal field stabilization energy, this starting material, you can think of the starting material as going to be lower in energy. So your activation energy barrier is going to be higher. And therefore it's going to be slower. And similarly, cobalt 3+, often cobalt 3+ is going to form, for many ligands, cobalt 3+ is going to form low spin complexes, which we just talked about. So again, if we have this D6 electron configuration, your crystal field stabilization energy, so you have this -12/5 delta octahedral plus 2 pairing energies for your crystal field stabilization energy. Again, this stabilizes your starting material and makes your activation energy barrier greater. So really quick example, hexaamine cobalt 3+. This substitution reaction, so we've got going from the hexaamine complex to the hexa-aqua complex, you can see here that our equilibrium constant is 10 to the 30th. That's a huge equilibrium constant. So we would say that this is a favorable reaction. So the large equilibrium constant tells us that delta G naught would be negative. So this reaction should favor the products. However, this reaction takes several days to occur. It's very slow. So this reaction is favorable, but inert. So we would say that this complex is inert to substitution. The synthesis of cobalt ACAC is a good example of using labile and inert to our advantage. So when we run this reaction, we start the substitution reaction with cobalt 2+ and form the +2 oxidation state of the complex. But this is labile to substitution. So we want to add hydrogen peroxide to oxidize it to form this cobalt 3 complex, which is now inert to substitution. Next, we need to talk about the chelate effect. The chelate effect simply says that the formation constant Kf increases as the denticity of ligands increases. So if we had two similar complexes, this is nickel 2+, here we have hexaamine, and here we have tris ethylene diamine nickel 2. What we would predict from the chelate effect is that the formation constant for this nickel 2+ compound with bidentate ligands would be greater than this complex with monodentate ligands. So let's look at the numbers. So if you have nickel 2+ and react it with 6 amine ligands in aqueous solution, your formation constant is 4 × 10⁸. So this is a very favorable reaction. But now let's compare it to ethylene diamine. Nickel 2+ in aqueous solution reacting with 3 ethylene diamine ligands results in a formation constant of 2 × 10⁸. If we think about this relationship, delta G naught is equal to negative RT natural log of K, we can make predictions about the difference in the change in Gibbs free energy. So this is the larger equilibrium constant. Larger equilibrium constant is going to result in a more negative delta G naught. So why the difference in favorability? Well, we need to remember this relationship from the second law of thermodynamics, that delta G naught is equal to delta H naught minus T delta S naught. So delta H, our heat, our enthalpy for the nickel amine bond and nickel ethylene diamine bond should be roughly the same. The strength of the bond should be similar because they're both nitrogens bound to our nickel. Very similar ligands. So the spontaneity of this reaction must be driven by delta S. So remember that entropy is a measure of disorder. Disorder increases as the number of microstates increases. So more particles equals more microstates, which equals more disorder. So again, if we compare these reactions, so this first one, remember that aqueous nickel isn't just by itself, it's probably coordinated to water in an octahedral fashion. So if we have hexa aqua nickel 2+ reacting with 6 amine ligands, forming hexaamine nickel 2+ and then 6 water molecules, you're starting with 7 particles and you're ending with 7 particles. Whereas if we look at this other complex, here we have nickel 2+, hexa aqua nickel 2+ reacting with 3 ethylene diamine to form our ethylene diamine that's displacing 6 water molecules. So now we're going from 4 particles to 7 particles. So we have an increase of our number of particles. Microstates is the number of ways that your molecules can be arranged or oriented. So if you think about it, this increase for just one complex ion of nickel, we have this increase of almost double the number of particles. So this is going to be a huge increase in freedom of motion. So when a multidentate ligand displaces a monodentate ligand, there is an increase in freedom of motion or disorder, which is an increase in your number of microstates or entropy. This is the chelate effect. The chelate effect is that greater formation constants for multidentate ligands because of this increase in entropy. Here are a couple other chelating agents. Here's EDTA. EDTA is a hexadentate ligand, and so is DTPA. DTPA is another hexadentate ligand. I use DTPA pretty routinely in my research to sequester iron, to prevent iron from undergoing chemical reactions with the species that I'm interested in, because iron is so ubiquitous. So there's always going to be some iron in your tap water. EDTA is used a lot for the same purposes. So EDTA can also be used to sequester iron. If you react aqueous iron with EDTA, the formation constant is 10 to the 25th. So this is a huge formation constant. And this is what you will see for these hexadentate ligands, is they form these very favorable complexes. So multidentate ligands can effectively form stable complexes around metals. Just a quick application of EDTA in the textile industry. So this is cochineal. Cochineal dye is bugs, actually. They're these little bugs that they're typically found on cacti. And this is what the bugs look like. This is some cochineal that I purchased for my chemistry and art class a couple years ago. So you can see the little bugs, and you grind these up and boil them in water, and you can get really beautiful colors from, this is specifically the compound. This is the carminic acid. So cochineal is a bug that lives on cacti that produces the carminic acid that can be used as a dye. The color of cochineal can vary if this dye coordinates with different metal ions. So here's the cochineal dye and the carminic acid. And the carminic acid, the oxygens on the carminic acid can coordinate to metal ions. This is one example. Carmine is two cochineal or carminic acid molecules that have coordinated to aluminum to form this really deep red carmine pigment. If you're trying to dye with cochineal, if you're trying to dye some silk or some textile, you want to make sure that you're able to control what metals are in the solution, because if you have your fiber and your dye, your metal can act as what's called a mordant, which will change the color. So in this picture, this is an experiment that my students did. Here's cochineal in deionized water, and here's cochineal in tap water. And so you can even see in just the difference between tap water and deionized water, the deionized water is a much more vibrant color and the tap water is a little bit muddier. And that's because the tap water has these different metal ions that are coordinating to the cochineal and altering the color. People that are working in textiles will add EDTA to remove metal ions from the tap water. EDTA is also sometimes used in water purification to remove metal ions from water. So in this lecture, we talked about crystal field stabilization energy, reactivity, the kinetics and thermodynamics of transition metal complexes, and the chelate effect. And we specifically talked about the application of the chelate effect to the textile industry, specifically with the cochineal dye.